Okay. Hi, everyone. I'm Deepti. I'm a software engineer at Google, and I'm here to talk to you about WebAssembly. So before we get started, how many of you have heard about WebAssembly? Oh, that's a lot of you. And how many of you have used WebAssembly? Okay, just the one then. Well, let's get started. So what is WebAssembly? Here's a snippet from the spec. WebAssembly is a safe, portable, low-level code format that's designed for efficient execution and compact representation. Now, that's a lot of words. What does that mean? Basically, WebAssembly is a compilation target for different languages like C, C++, Rust. Most recently, there's been some work in Kotlin, Go, and some other languages that have announced experimental support. It's an abstraction over the hardware and is language and platform independent. And because it's a compilation target, it's not something that you write by hand, or it's not something that you program in, but it's something, it's a format that tools generate for you. One of the reasons it's been gaining traction is that a number of implementations and compilers are targeting it for use in web programming. So a very common use case is that if you have an application that is written in any one of these languages, you can compile it to WebAssembly, write some JavaScript code with it, and use it on the web. Now, I want to draw attention to a couple of the design goals of WebAssembly. The first, that it has fast, safe, and well-defined semantics. So it's fast because it's designed to take advantage of capabilities that are available across modern contemporary hardware. It's safe because the code is validated and executes in a memory-safe sandboxed environment. It's well-defined. That goes to say that it's designed to minimize some of the non-determinism that's an essential part of, that's something we see in other languages. And it has a predictable performance model. The other thing is that it has an efficient and portable representation. So when you have a WASM module, all the module information is represented using a dense binary encoding. So compared to a textual format like JavaScript, that means smaller files, faster decoding, faster loading, reduced memory usage. It's portable in the sense that it doesn't make assumptions about the underlying architecture that are not already common to modern architectures. Now, the WebAssembly MVP is supported on 4 major browsers, like Chrome, Firefox, Safari, Edge all have WebAssembly support, and Node.js and other embeddings as well. The thing that's really exciting to me is, The thing that's really exciting to me is that it's developed in an open community group. So WebAssembly is standardized as a part of the W3C community group. So if you think that this is something that's not, that if you have a use case that's not commonly supported, or if there's something more that you want done there, you can file a GitHub issue on the repository or come talk to us at one of our bi-weekly meetings. Just one second. So the next slide has some screenshots of non-exhaustive things that have been really interesting to me over the last few months. The one on the top right is the blog post that was published when Unity first started supporting WebAssembly officially, so it's out of experimental. They made it possible to make WASM-only builds. So the ASM.js suite is maintained, but now every change that goes in there is tested against WASM as well as ASM.js. The one right next to it is the tweet about AutoCAD, the AutoCAD team sent out when they ported their 35-year-old code base and got it to compile in a browser using WebAssembly. So what you can do is you could just click on a link and then go use AutoCAD. So all of the power of AutoCAD is just a link away. The one that's next to that is the Cloudflare blog post about extending workers with support for WebAssembly. It's another case in point for WASM being used for resource-heavy tasks. So if you were interested and you wanted to go look up that blog post, there's also a neat little demo there for dynamically resizing an image that using WebAssembly, and the source code is attached to that as well, so you can see what's going on. The one below that is Virtual 3D moving from pure JavaScript to a combination of WebAssembly and JavaScript, and their improvement in page load time. The one next to that is actually really interesting. So it's 2018, so I'm going to talk about blockchains for a second. WebAssembly has now found a home in blockchain VMs. So it's by design, WebAssembly minimizes a lot of the non-determinism, and each WASM instance has its own separate memory. So these are all design choices that are conducive to being used in the blockchains. Now, I just want to make a quick note here that I've been talking about, performance and WASM's faster and JavaScript. Some of the JavaScript's replaced all of that, but the point I really want to make is JavaScript and the web APIs have created like this really powerful web ecosystem. And what WebAssembly is trying to do is to add new functionalities to the web. It's in some cases there are existing code in JavaScript that had to be rewritten because there's no other way to do it. Like right now, the only thing you can do is use JavaScript in the browser. But it's just what WASM is trying to do is basically, give you a way to use existing code bases in the web. So even though one of the primary goals of WebAssemblies is to bring a new class of applications on the web, it doesn't make any web-specific assumptions or provide web-specific features. So the core specification itself can be embedded in many different environments. So what about WebAssembly and Node.js? WebAssembly modules can be imported into a Node.js app exposing WASM functions for use via JavaScript. WASM on the server allows you to ship like a single binary to any platform. So you get some portability here, so you can compile once and run everywhere. Or even if you were looking for code reuse, you can run the same code on the server and the client without having to recompile. There's also security. So like I was talking about in a couple of slides ago, one of the design goals is also that it runs in a sandboxed environment. So each WASM module executes within a sandbox environment, which is separate from the host and runtime using fault isolation. Now, applications execute independently and can't escape the sandbox without going through the right APIs, and they have to execute deterministically and with limited exceptions. So each of these modules is also subject to the security policies of the host environment. So in the browser, that would be restrictions based on the same origin policy, or on a non-web platform, that could include the POSIX security model. So for Node.js specifically, I want to mention that it is not faster than using a native library. It's not faster than native. It's not, the speed goal here is to be near native. There's no direct access to other Node.js modules and native libraries. The portability and security that we've been talking about comes at a cost. So, for the application, that's a trade-off that the developer has to make about what that should look like, whether the cost of the portability and security that you would pay in terms of speed is worth it to you. So we talked about reusing some of the existing C, C++ libraries and not having to rewrite them in JavaScript. And I also talked about the previous example of Autodesk being able to compile a 35-year-old code base to work on the web. Now, I realize the reason I asked the question ahead of time about how many of you used WebAssembly is I think I want to walk through one of the practice examples of what this would look like in practice and how you would use it. And again, the whole back to 90s slide is there's so much code out there in C, C++, libraries that use, that are developed for image processing, for cryptography. These are things that you could just port to WebAssembly and import into your JavaScript application without actually having to rewrite them. So for this exercise, I picked CIMG. It's a small open source C++ toolkit for image processing. Its development began at the end of 1999. It's self-contained, it's thread safe, and it's really quite portable. It fully works on different operating systems. It's lightweight. It's made of a single header file that has to be included if you were to use it. The other nice thing is also that the API it uses underneath was kind of easy to parse through. So there's just a class that has CIMG, and what I'm looking for is a data buffer, and that was actually readily available. So it was easy for me to see, okay, if I want to port this, I know what this class looks like, and I know what I need to expose to JavaScript to play around with it or import in my JavaScript code. So let's walk through what you need to get this all working. So we started out with the CIMG header file, or there's whatever code you would choose. So when we started out with this header file, there were also a bunch of examples in the repository. So I was looking for something that would be easy to compile, easy to port, and something that would be just fun to play around with. So the first thing you need is you need to set up the tool chain. So you need a tool that will compile your source code to WebAssembly. One way is to use the LLVM compiler tool chain. This can be set up to work with different languages, but for C, C++, you can use Emscripten, which is an LLVM-based tool. So for setting up the tool chain, the easiest way to do this is to download and install the portable Emscripten SDK. It gives you the whole Emscripten toolchain. It gives you Clang, Python, Node.js, and some Visual Studio integration too, in like a really simple, easy to install package. So it's like 3 commands, grab a coffee and come back, and your toolchain will be set up for you. The other thing is, what you have to do next is you have to identify what you really want to build and how you want to expose that to JS. Now, I was looking through, there's this whole big set of demos and examples in this repository, and some of them are a little more complicated than others, so I picked an easy one, which was, okay, I'm going to have an item that's filled with triangles. Now, this could mean, basically what happens here is I saw this code, but it's not something I can expose to JavaScript without actually doing some work. So there's a little bit of work you would have to do to understand how to restructure that. In my case, the only thing I had to do is refactor the code a little bit so it's not returning the pointer to the entire class, but just the data buffer. What I was trying to say was, if there's an easily exposable API, you won't have to do that much. But if it's hard to find, you might be signing up for some minor refactoring work. So now when you use the Emscripten compiler, you have a standalone WASM file. The standalone WASM file won't do anything by itself. So we need to load it into some client JavaScript code. So you have to figure out what APIs make most sense for your use case. There are different ways to do that. I'm using mbind to bind C++ functions and classes to JavaScript so that you can access your compiled code easily in a more, maybe not easily, but in a more natural way from JavaScript. And you need you need to give it some bindings code so that it knows how to call that function from JavaScript. So that's JavaScript integration. Now on the web, I also need some HTML glue code. So I've included, so this compile JavaScript, I would just call from the script tag in a sample index.html file. And I would I started a Python simple HTTP server and navigate to the port. And then I saw, sorry, I'm gonna come back to that. But there's basically, it would display something on there. Now for Node.js, this is more of a web-based example, but if you were looking for something you want to do in Node.js, you could pick a different example or a library to compile. Like if you wanted to decode an image or compress an image, that's something that you would be able to compile to WASM and then use from JavaScript, and then that JavaScript code you could just run in Node. So these are just snippets of commands that I used, which was just the first one is a snippet of a command I use. So if you look at it, that's em++ with some options. This command will generate both a triangles.js and a triangles.wasm file. So I'm using Embind here, which, like I mentioned before, it needs like emscripten bindings blocks to create bindings for functions, classes, value types, pointers, any of those, which is the reason I have the bind option that I'm passing to the compiler. I'm also using add-on post-run here, which is a runtime function. So I need extra exported runtime methods to access that function. The next screenshot is a part of the script in the index.html file in like the add-on post-run method that calls the function to get the image after the triangles are drawn on the background image. So some of this might look daunting in the beginning, but there's a lot of documentation out there, especially in the Emscripten repository, for how to use these options, what makes sense, how can you expose C code to JavaScript. So if you're interested, I would encourage you to try it out. So what I get here is different tiles, and I have 5 triangles in each tiles. This in itself is not, it's not doing that much. But there's a lot more you can do here. So these were just like, this is a minimal, just a one compiler command and then some glue code to make it run. So this is fairly straightforward. But there's a lot more you can do with it. You can intercept mouse clicks, or you can, add rotations or add speeds and different triangles and different colors. So those are all things that are available that you just have to look for in the repository and then port. And this particular library was actually standalone. Sometimes there are libraries that depend on other libraries, so you have to be aware that if those are not already ported to WebAssembly, that's something you might have to do as well. The fun thing that you could really do with something like this is maybe build your own photo editing app. Now, a lot of the code for decoding, zooming, adding blurs, that's all available. So because this is just like, you just have to include the header, and all of this library is available to you. So there's a lot of room there to play around with. And these are not algorithms that you have to re-implement in JavaScript. You could just port them over from C and use them in your application. So we talked about how WASM is generated using the tool chain. Let's take a look at what happens inside of V8. So before we get started with what happens to WASM code in V8, I want to take a quick look at the JavaScript pipeline, because it's easier to compare what happens on both ends. So here's an overview. The process begins with a script coming in. I didn't actually include that little box there just because I wanted to talk more about this particular diagram. It comes with a script coming in from the network cache or an extension or an app. And the script text is processed by the parser, which then makes an abstract syntax tree. The tree is walked to generate bytecode for the interpreter ignition. The bytecode is then interpreted. Now, as the bytecode is running, there's a lot of type feedback that's collected. When a function is hot enough, the type feedback and bytecode is used to feed the optimizing compiler turbofan, and turbofan then, has different lowering passes. I'm glossing over a lot of these details, so some of my V8 colleagues are maybe looking at me like, what are you saying? But so the machine code is then, turbofan is walked over, you have optimization passes, and then the machine code is filled with assumptions, and then the machine code is generated. The machine code that's generated has a lot of assumptions about type feedback. So if any one of these assumptions is violated, then you have to fall back, and you trigger the-optimization, and it kicks things back to the interpreter. So this is just like a very high-level overview of what happens to JavaScript code. Now, when you have WASM code, now we know how the WASM file is generated. So the only way the WebAssembly module can get to the V8 engine is through the JS API right now. There's a proposal for adding a C API for other embeddings, but that's still in progress. So what you can see here is that it skips a bunch of the passes, and it creates a graph directly. The graph is still, you could still optimize the graph, but that's not really the point, because what you did initially was to use a compiler to generate the WASM code. It goes through LLVM, so LLVMs, we're kind of moving ahead with the assumption that LLVM already generates optimized bytecode, so you don't need to optimize too much over that. And the other thing that you would notice is that we don't rely on type feedback. WASM is statically typed, so there's not a lot of type feedback and de-optimization that's involved. So it has a more predictable performance model. Yeah, and the other quick thing is that it's just there's two compilation pipelines where there's a baseline compiler that generates baseline code, and it can defer back to the main turbofan compiler and generate optimized code. So before we move on, I think I want to talk about performance caveats. I've been talking about how things are fast, things are optimal, loading is faster. All of these things are, they're true, but performance is nuanced and it's tricky to measure. So, and also that WebAssembly is an emerging standard, so there are still cases that, things don't quite work the way you'd want them to, but we're working on fixing the spec for that. And the really nice part about that is that all of the engines on board are also supporting making this better. So we get a lot of questions of, will this application be faster in WASM? The answer to that is always that it depends. Now, if WASM really shines when you have resource-intensive tasks, so if you have image decoding, video processing, game engines, anything that is self-contained and performs a lot of computation, those are the kind of things that would be really fast in WASM. Now, if you have an app that does a lot of lightweight JavaScript calls and interacts heavily with the DOM, those are the things that, that might not be that fast. We're also working on having host bindings, native host bindings to WASM and the DOM. That's still way out into the future, but when we get to that point, then that's when these things will be faster. The WebAssembly MVP has been out there for a little while now, and I want to talk about other proposals that are in flight and that are being worked on. So this is the one, personally, I'm really excited about. The WebAssembly threads feature allows you to have multiple WASM instances in the same web workers to share a single memory object. Just like shared array buffers in JavaScript, this allows really fast communication between workers. You can use this to offload computation to another thread to keep the main thread and its UI responsive. Actually, I think I don't know exactly. what I said. I think I said that the feature allows multiple WebAssembly instances in the same worker. What I meant was multiple WebAssembly instances in separate workers, so different workers share the same memory underneath. The proposal adds low-level building blocks for pthread style shared memory, so you have shared memory between threads, atomics, and futexes. Now, a lot of the code that's pre-existing, a lot of the C libraries extensively use threads. So this actually simplifies the porting experience quite a bit. Otherwise, you have to jump through hoops to emulate that, and that doesn't always work. So as a developer, this is also something that you could just use right out of the box without actually having to worry about it if you're porting an application, if you're porting a multi-threaded application when WebAssembly threads are supported by your engine. These are some other future features and proposals in flight. So we have SIMD, which supports 128-bit vectors and uses vector instructions, which are widely used for image and video processing, cryptography, etc. These are basically just like, again, goes back to the fact that a lot of WebAssembly is an abstraction over the hardware. So a lot of the Intel and ARM hardware have vector instructions, and we're trying to find a nice way to expose that to the web. The other one is exception handling. So in a web environment, exception handling can be emulated using JavaScript exception handling, which can provide the correct semantics, but it isn't always fast. So there's a lot of ongoing work to explore zero-cost exceptions. What this means in practice is if you have C, C++ code that relies on exceptions, this would make this go faster. And the other interesting one is garbage collection. We've seen a lot of C, C++ code, but what about higher level languages? To use any of these higher level languages and port to WebAssembly, you need garbage collection support. So that's also something that's being actively worked on. There's tail calls, host bindings. ECMAScript module integration also is quite interesting. So there's an ongoing proposal for WASM modules to be interchangeable with ES6 modules. The idea is that the module entry points could also load WebAssembly modules just by passing the URL of the WASM module. So there's more proposals in flight, and if you want more details about what these actually look like, there's a link below there that you can follow. Okay, thank you. And here are some resources and code labs. So I know most of you haven't used WebAssembly, so there's some fun code labs that you can follow through. And there's a link to the community group and webassembly.org. Thank you, everyone, for attending.